So these modeling kits. So here's mine, for example. Black is carbon, blue is nitrogen. Here you can see like a 6-membered ring. Red is oxygen. And the way these work, I'll just pull off the last carbon. Well, I guess I don't need to share right now, make it bigger. The way these work, these is you pull them apart. So there's the 109.5 angle, and then they snap together, and then you can put little spheres on the end or connect it to the next carbon. It looks like, if we go back, more of it these days, or at least when you search on Amazon and Google and stuff, you get more of these kind, where the balls are, the spheres are the atoms, and then there isn't like a lone pair. There's just no place for it to plug in and make a bond. So these are maybe a little more, you're forced to do it correctly, so to speak. But they're about 20 bucks, it looks like, you know. And then here you can see different molecules. And I mean, this is OChem. We don't know the names of them yet, but if you're going to buy it, if you got to take OChem, you really need this. It's only 20 bucks. And this is when you're learning it. So you may as well just buy it now. And to be honest, you won't really need it in Chem 162 much. So I wouldn't put it off like for next semester. There's kind of no point. All right. Did it switch? I think so. Let me bring back. Chat. Okay, we left off here where we had gone through all these different shapes. And we had no lone pairs on the central atom, right? And this is the VSEPR theory. You get it to full screen. Okay, so what happens when there's a lone pair instead of a bond? So the lone pair, it still is an electron group. And so it still occupies space. And in fact, it actually occupies more space because it's not bound and attracted and held between the two nucleus. So it actually has more space and pushes out on the other bonds. And so the order of this, as far as size, is when you have, two lone pairs together, a lone pair pushing bonding pairs, and then what we'd already covered is just normal bonding pairs, where these were essentially all equal except for maybe the radius size of the atom. And for most of these, you divided 360 by whatever number of atoms. All right, so what it's talking about is this is where the lone pair would be, right? That's the nucleus. So when the electrons are confined between two nucleus in a bond, it takes up less volume than if it's just a lone pair. So this is where the balloon models kind of fail a little bit. All right, then what this is all saying, I'm not going to read it all to you, is just that those lone pairs have an effect on the geometry and they distort the angles a bit. And we'll see how that comes into play. It'll be important sometimes and not terribly important others. Okay, so we don't need to start off with linear. If you remember, the example for linear was like CO2, is if it's in a straight line, the lone pairs can't push it or do anything. So it doesn't really matter for linear. So that's why it's skipping it. All right, but if we go back to the next shape after that was trigonal planar. So when there's a lone pair there, not terribly difficult or, hard to remember or a big change. It's just called trigonal planar bent. And so an example of that is SO2. Right, here's the SO2, the way we learned about it last chapter, the resonance. And this is what it looks like in reality, right? The double bond and single bond are flip-flopping back and forth. You can even draw this structure over here, but the two on the left are better. We covered that with the resonance. But the important thing is that there's the lone pair there make a third electron group. And so above the yellow sphere is where the lone pair would be, and it pushes the two oxygens down. And this will become important why that it's not actually linear like it's drawn in the Lewis dot above, but like the model shows, that it's got this bent structure. All right, so the way these go is basically we move on to the next shape where there's another lone pair and successive more lone pairs on there, right? So on this one, right, if the central atom sulfur had another lone pair on there, it would just push it further, but then that would be 4 electron groups. So this is still trigonal 3 electron groups. Okay, so move along to the tetrahedral electronic geometry. Then that means, remember, right, there's 4 electron groups around the central atom, but now one of them's a lone pair. So what does this do? It's basically your tripod for a camera, if you're when a photographer is taking a picture, that kind of thing, or if you had a telescope on a tripod. So it's called pyramidal. And then if there's another lone pair, so 2 bonds and 2 lone pairs, which is going to be oxygen, we'll see a lot. This is water. It's tetrahedral bent. This has to be planar because it's just like the SO2 we saw before, but with 2 lone pairs, so it's pushed. So the bond angle should be around 109.5, but it's less because of the 2 lone pairs taking up more space. And the classic examples of these are group 5 things like nitrogen and phosphorus. And this one doesn't show it as dramatically. And part of it, I think, is because they picked hydrogen. But if these bonds were longer or was, an atom bigger than hydrogen, for example, the blue sphere would be up further off the ground and more like a tripod for a camera or something. This picture is, a little bit better. So here's what we learned before, right? The nitrogen has tetrahedral electronic geometry, but then when you look at it in reality, the 1 electron group is a lone pair, not an atom, and it pushes down more, and it's distorted from the 109.5. It's around 107. The degrees and the pushing past normal isn't terribly important. The general geometry is, but not these. You don't need to memorize 107. But the important thing here that we'll see coming up with polarity and the bonds is that if there was 4 things there, it would cancel out. If there's 3, the molecule's no longer as symmetric, right? The nitrogen's above the 3 hydrogens. And this goes back to that, like, pyramids in Egypt, when they buried kings, they buried them in the center of the volume of the pyramid. And that's where the nitrogen, the central atom, would be. Okay, so again, moving on. 1 less bond, 1 more lone pair. So now there's 2 lone pairs at the corners of the tetrahedral. So we're reduced to just 3 atoms. And whenever you have 3 atoms, it has to be either linear or bent. You don't really have much an option. So then it's just whether there's lone pairs there. And so for water, this is important especially in the sense that water looks like this with this bent structure, and it's not linear. And this has huge effects that you will see the next few chapters, and on boiling points and melting points and all kinds of things. AS is arsenic. It's directly below phosphorus, so not surprisingly that it behaves pretty similarly. And this is the model's kind of funny looking, but anyway, the lone pair would be on top, and it has that tripod kind of bent structure, or tripyramidal structure. So again, here's water. You don't need to memorize 104.5. Just the important part is to know that that those lone pairs are there, and it distorts and makes the molecular geometry different, right? So the electronic geometry sometimes you see in these books, which they teach it to you when you're learning, but after you learn it, no one reports it the electronic geometry of tetrahedral. It's the actual geometry that is important. So another example, chlorine, right? The oxygens are -1, the chlorines plus. And so there's two of them, so the oral's -1, there's our formal charge. The lone pairs make it look just like water, right? So 2 set to lone pairs, 3 atoms in a row has to be linear or bent. If there's lone pairs on it, it's obviously not linear. Okay, when there's lone pairs on the trigonal bipyramidal, it gets much more complicated. I'm not going to put one of these on the test. The reason for this is almost everybody's going on to take OChem, and you won't ever see these in OChem. It'll never show up on a test. So only chem majors, I believe, would ever see these again. So it seems just a little excessive, and we don't need to spend a lot of time on it when no one's ever going to see it again. And the molecules aren't very common. So the ones that we just covered up to are like, you'll see them in OChem and also water and boiling points and stuff. But these ones here, right, so if there's 5 and a 1 lone pair, it's called a seesaw. Then if there's 2, it's a T-shape, and then 3, it's linear, and it's easier to see it than to describe it there. And so the reason it's called seesaw is if you imagine you turned this one, it would look like a seesaw in a kid's playground or something. And the reason for this is the lone pair takes up more room. So if it's here in this spot, then these 2 fluorines are 120 degrees away, and these 2 fluorines are 90 degrees away. On the right, on the left, if the lone pair was up top, then you'd have 3 fluorines that were 90 degrees. So it's just, since the lone pair wants to take up more room and is more repelling, it takes this spot over that spot, and then you get the seesaw. All right, and there's a couple of examples like this. So if you're going through the book or doing other problems somewhere, you'll come across these. But like here, this SF4, I can't even tell you off the top of my head what this molecule gets used for. So, all right, and then here they're showing you the seesaw shape, right? This kind of looks like a teeter-tot or a seesaw. And I think it's a little silly to put something on an exam when I can't think of examples that you would come across in your everyday life. And some of these you wouldn't even see in organic chemistry. You won't use this molecule, for example, in OChem. So again, only chem majors would need to know this, and in future classes, not in ours. Okay, so if you add in another lone pair, again, the lone pairs take up more space, so they're going to go wherever they can that has more space. So the next most reasonable one looks like this. And you can see, it's not that sophisticated of a name. It's just called T-shape. Right, then, another example. Again, another molecule that I don't think anyone will ever come across, and I can't think of what this is used for. Then if you have 3 in there, it's linear, right? Because they want to take up where they have the most room. And in this situation, then the fluorines are, you only have 2 fluorines in there at 90 degrees to all 3 lone pairs. All right, so that one's a little complicated because of the unique shape. The octahedral one, again, I don't think you'll see it in OChem. And again, it's just for chem majors, so I'm not putting one of these on the test. But this is much more similar, or similar, it's much more simple. So it was octahedral, and then if there's a lone pair there, then this is just a pyramid with a square-based pyramid. So the one lone pair, that's pretty easy. All 4, if we look at the lower model here, all 4 green atoms would be in the same plane, and then one up top. And that's just a simple pyramid with where the base is a square. And so that's what it's called, the square pyramid. And then when you add in another lone pair, you remove, in this picture here, the lone pair would then take up where the top of the pyramid is, the fluorine. And so you get what's called square planar, where all 4 atoms are in the plane of the central atom. And xenon F4, I don't know what that molecule is used for. So I'm not going to focus or put on the exams anything where there's 5 atoms attached to the central atom, or larger, or 6. No 5 or 6 electron groups are on the central atom. This is mostly meant to prepare people for OChem. So what that means is table 10.1 is really your sort of your cheat sheet and what's important, because notice, right, electron groups, it goes up to 4. So these are the ones that you're going to see and use. They didn't, BF3 isn't quite the best example, but you'll see BF3 in OChem. So electron groups get you to the original geometry, but then what's most important is the molecular geometry, right? This is what's you're going to be asked on the test, is the actual geometry. So what's most critical that we take away from it, the example-wise, is the difference between water and CO2, right? So carbon's in the middle, 2 double bonds, it looks linear. And last chapter, you might draw water, H2O, looking like this. But now we know from this theory here in the lone pairs that it's really bent, right? And this has profound effects, right? Water, for example, is a liquid at room temperature and pressure, and CO2 is a gas. CO2 actually sublimes. It's never liquid at 1 atmosphere, and that's what you'll cover in Chem 162. Why 2 molecules that seem so similar in the bonds or the chemical formula, but what you just learned here is the structure, and we'll see how the structure is the reason that ice floats and the boiling point that it has, and the high, water has such a high freezing point for a molecule with such few atoms, and it's due to this bent structure and the lone pairs. Okay, so you obviously know the testing format for this class, where there'll just be pictures up and you pick the corresponding group and whatnot. So similar to the last test, but for people that have to take OChem, I would highly recommend getting used to this process here, where you actually draw the molecules yourself, because you're going to have to in OChem. All right, so we covered this last chapter, but you really should do these problems. It's really good too when you have it, not necessarily the day after class when you've just seen it, but a day or 2 later. Come in and see if you can do these problems in the PowerPoint when they're active, because it gives you hints, and it doesn't show you the full answer right away. All right, so the Lewis structure was last chapter. Obviously, you have to do that right to get the number of groups around the central atom. Right, then you need to know what's bonding and lone pair. And then you can use the table, obviously, if you want, but as the molecules, especially in OChem, as they get bigger and more complicated, you're not going to have time to look at a table. Like, you need to have it memorized. It's kind of like, especially in OChem, it's like your phone number. You use it and know it so much. It just becomes, you didn't sit and like try to memorize it. You just used it so much. All right, so this isn't the type of one that'll be on the test, but the procedure is still the same. We're like, right, it's SF5 minus. So we're going to have silicon in the middle. We're going to have at least 5 groups around it. How do you know what element is the central one? Well, it's the least electronegative. So between fluorine's the most. So this one's kind of obvious. Silicon's in the 3rd row, so it has the expanded octet. So it's the obvious choice. It can make, it's got access to the d orbitals, and it can make more than just 4 bonds or 4 electron groups. Silicon's got 4 electrons. Fluorine has 7, but we have 5 of them. And then the negative charge tells us 1 extra. So for a total of 40. All right, so draw the 5 bonds to silicon. Then take all the leftover electrons and start adding them in on the fluorines. Right, so the 5 bonds, 2 each, that gets you to 30. And then the 6 electrons as lone pairs times 5 is 30. 10 plus 30 is 40. So we used them all up. So in this one, there's no electrons, no lone pairs around the silicon. So 5 electron groups on silicon, all bonding, no lone pairs. So it gets us that weird shape, that trigonal bipyramidal. So this is still a good exercise in the procedure of going about it, but I'm not going to put one of these on the test. We're going to focus on the tetrahedral ones. Should probably change the animation. It shows you the model beforehand. All right. Of these, how do you know which one to make the central atom? So it's definitely not fluorine. It's the most electronegative. Oxygen and chlorine, they're 1 away from fluorine, so you might not be sure, but chlorine it's in the 3rd row, so it has access to d orbitals, and so it can form more bonds, where oxygen can only form 2 and fluorine 1. So I mean, you're only left with chlorine or oxygen as which is going to be the central atom, but oxygen doesn't really make sense. It only makes 2 bonds. So chlorine makes more sense. It's got 7, oxygen has 2, has 6, and there's 2 of them. And the fluorine has 7, you add that up, that's 26. Let's make chlorine a central atom, attach each oxygen, and then start filling in lone pairs around, and we get this kind of structure. So the chlorine in the middle, 4 electron groups, 1 lone pair, 3 bonding. And that gets us that trigonal pyramidal shape. Most common with nitrogen and phosphorus in molecules and atoms and whatnot that you'll see, but still, there's other possibilities like this. All right, so they're ballpark 109.5, but they should be less because there's a lone pair up there pushing them down, but something like that. So this is your tripod for, you put your camera on top to take a picture, that kind of thing. Okay, more beginning of organic chemistry. So if you've had an art class where they taught you how to draw 3-dimensional things on a piece of paper, this is sort of that. Or if you've had a CAD class, CAD is computer assisted design. It's sort of, it's drafting, which is an old form of architectural plans, basically. So if you've had any classes on that, then you'll be kind of familiar with this. And this is just a way of drawing chemicals on a two-dimensional piece of paper, but implying the three-dimensional nature of the molecule. All right, so a straight line is a bond where between the two atoms where it's in the plane of the paper, or a bond or something that's coming towards you out of the paper. We use a solid wedge, and then they use a dashed or hashed wedge for ones that are going away. So let's start up here at the top, right? Linear, this CO2 was our classic example. This, it all has to be in the same plane, right? Because it's 180 degrees. Trigonal planar, it looks like a fan, right? That has three blades, or the propeller on a plane or something, right? They're all in the same plane. Bent, so this is water, H2O, for example. It obviously has to be in the same plane because there's only two bonds. There's no way. So just like linear, but it's got a lone pair. Whether there's one or two lone pairs there, it doesn't matter. All right, tetrahedral here, this is the one that I pulled up on mine. So if I put my camera on, let me move it where I can see it. So if I rotate it, right, that one, it looks like a dot almost. It's coming right at you. And then as I turn it, right, the 109, so now it's not right at you. You have to angle it. Whoops, angle it more. Now that one looks like it's coming at you, etc. So there's sort of the pyramidal shape. And so the way you can show this on a piece of paper, two-dimensional with these wedges, is that the two XA bonds, that's in the plane of the board, and this X is going away behind us, and then this X, the lower right one, it's coming out towards you. The one next to it, that's drawn pretty well. They chose kind of a weird angle here at the trigonal pyramidal one. I don't know why they did that, but it's fine. So the trigonal pyramidal, this X back here on tetrahedral is the one that's missing. That's where the lone pair would be. So it's just drawn a little weird. Normally, like we saw when they introduced it, the three X's would be on the ground, and the A in a plane, and the A would be lifted up above it. Then here's the trigonal bipyramidal, right? The X's are 180 degrees, so they're going to be in the same plane. And then it doesn't matter which one you pick. And you can draw the mirror image of it, and you'll do things like that in Chem. But so those three X's are in the plane, and then the two on the right, one goes behind and then away from you and then out at you. Then here you can see, the seesaw and the octahedral and square planar. And I won't, our focus is going to be the linear trigonal planar bent and tetrahedral, because that's carbon and simpler elements. And that's mostly what, 99% of organic chemistry, which is generally why people are in here. All right, so then just a few more pictures of this. And they have these things called jacks where like kids would, well beyond my time, like in the 50s, 1950s or 1960s, you would bounce like a rubber ball and then try to pick up a number of these. And they were, like bigger than a staple, but kind of like the size of your thumb. I don't really understand the fun of it or the game. But anyway, these look similar to that. And iron, this is important in the sense that like iron that's in your blood, myoglobin and hemoglobin, is bound like this, where it has nitrogens in this plane, and then I think a histidine residue on the bottom, and then the oxygen that we breathe binds on top where the top fluorine is. So for bio people, you'll see this again, but not until you get into a bio class, and they're not going to ask you, as much about it, and it'll just be, in that class, and you can kind of relearn it there. But everything else below, carbon based, this stuff is incredibly important as you build carbon molecules, which is basically here what this next slide is, right? Slide 55. Multiple central atoms, instead of all these that we've covered here, where there's just one central atom. I don't think we even saw one with, 3 or 4 bonds in a row. But, vitamin C, nicotine, caffeine, you name it, anything amino acids, everything is a combination and a building up of these individual carbon, nitrogen, oxygen things. And each atom then becomes your central structure, but they attach to one another and they build up, right? So you can think of them having multiple central atoms. You describe the shape around each one. So here, for example, this is called acetic acid, and it's vinegar, right? So if you cook with vinegar, my dad has this crazy theory that he drinks a cap full of vinegar every day, thinking it's going to stop him from getting arthritis. I don't know. We'll see eventually if that works. I think, he plugs his nose and forces it down. It doesn't look like much fun to me, that's for sure, but hopefully it pays off. So the beginning of OChem here is going to be where you go through and basically perform this type of operation that we just went through on each individual atom. And then, as you take, this is the first week or week 2 of OChem, and they're going to expect you to master it and be able to know it all year long. Right, so this first carbon, it's got 4 electron groups around it, all bonds, so it's tetrahedral. And carbon never has lone pairs around it, so it's not an issue. Then the next one, with the double bond counts as 1 electron group, so it's a single and 2 doubles, so that next carbon is trigonal planar. And then not much to say about the oxygen with the double bond, right? Because it's like hydrogen, it's capped, there's nothing else there. Then this looks just like water, H2O, so it's going to have that tetrahedral bent structure. And then here they'll show you what this looks like. Now there is some flexibility. These bonds can twist and spin, but it still has this general look. And this is where those models get handy. This was pretty easy, right? You could call it 2 carbons and the 1 oxygen. It's only 3 central atoms, but in OChem, you're going to start building up and making much bigger molecules. This one is methanol. This is not the alcohol that humans drink. This one actually, moonshiners that make alcohol illegally, occasionally they go blind, and the reason for that is they're making the wrong alcohol. They make methanol, and so the enzymes in your body chew this up and make something called formaldehyde, and that makes people go blind. So it's not the methanol directly, but the enzyme oxidizes this. Anyway, our point here is the carbon has 4 single bonds around it, and that's tetrahedral, and the oxygen, again, looks like water. It's just bound to carbon where the 2 lone pairs are there. So on the left is how we thought about it last chapter, but on the right, now after studying and knowing via CPR, we know what it really looks like, right? The oxygen's bent. Right, and so glycine is like, the simplest amino acid. And again, more central atoms, right? The nitrogen there has a lone pair on it, so that's that pyramidal shape. Carbon with 4 bonds, so tetrahedral. This carbon has 3 electron groups, single two singles and a double, so that's the trigonal planar. And then, not too surprising, water is always going to be either a capping situation like this with a double bond, or two singles and so bent. Right, and then here's, putting that model together. This hydrogen that I'm moving the mouse on is a little peculiar because it's coming directly out. You can't see the bond. This one, if it was three-dimensional, would be coming at you. This hydrogen here as well, but the way this one's drawn is slightly confusing. And this is where, as molecules get bigger, these get more and more handy, and so very useful in OChem. So let's do a few problems. This is kind of one of the exceptions, right? Because there's boron in there. How do you know what the central atom is going to be? Well, hydrogen's never the central atom. It only forms one bond, right? And it's terminal. Oxygen isn't really ever the central atom either, unless it's, water, which this is clearly not water. So odds are it's going to be boron, and the math works out pretty good that boron usually wants to form 3 bonds. It's that one exception. It can occasionally form 4 as well. So boron seems like it's the least electronegative too, and there's no way it's hydrogen. So you're really just picking between them. Valence electrons, boron's got 3, carbon has 6, and we got 3 of them. Hydrogen has 1 and 3 of them. So you add all those up, and that's 24 electrons, right? Put boron in the middle, connect the oxygens. Hydrogens are always terminal. Then you fill in the lone pairs around it, and there's no electrons left over for a lone pair around the boron. The oxygens all have 8 electrons. They're happy. The boron has 6, but it's fine with that. It's one of the exceptions. So this is 3 electron groups, no lone pairs, and that's trigonal planar. Right, the oxygens all have 2 groups and 2 bonds, and that's that bent shape, or specifically tetrahedral bent. But bent is good enough. Doesn't really matter to me, tetrahedral versus triangular bent. And here's what it would look like. And this is boric acid, which has some common uses. You might be able to find that under the sink in your kitchen. Okay, so why do these things matter? They matter because it changes the behavior of molecules depending on their structure. So the big example was carbon dioxide versus water, right? And how does it do that? It does that from the polarity of the bonds. So the polarity, remember, is the electronegativity difference. Then you measured these things, they're called dipole moments. And if the molecule's symmetric, they all cancel each other. But if it's unsymmetric, then we have what's called vector addition. Right, so intermolecular forces means the interactions from one molecule to another. And basically, this is what determines boiling points. Solubilities, remember, that's whether 2 things mix together, if they like each other. So if you've ever, been in a boat harbor and you see oil or gasoline floating on the surface of the water, it's because they don't like each other, right? Water has OH groups and is polar, and gasoline and oils are mostly carbon-carbon and carbon-hydrogen bonds, and none of those bonds are polar. So this is where those non-bonding, those lone pair electrons can come in and affect the polarity and have huge effects. All right, so remember what this looks like. Partial positive on the less electronegative, partial negative on the more electronegative. So simple example is HCl, where it's polar and the electrons are pulled towards the chlorine. And the way you draw these usually is you put a little positive sign near the less electronegative atom, and then a little negative sign near the more electronegative, and then you just connect it and make a little arrow. Okay, so what is vector addition? You've done this before. If you've ever swam in the ocean against the current or with the current, if you've walked on an escalator, with the escalator, or the people mover ones that are at like airports that are flat. So if you're going, up the escalator and you walk with it, if, let's say the escalator is going 5 miles an hour and you walk 5 miles an hour, then your overall movement really becomes 10. And this is kind of the way tugboats in harbors move big giant boats around, right? When a big huge ship comes into a harbor, its engines are not capable at making sharp and little turns and twists, and so the tugboats either push on it or hook up ropes, and they move it more slowly and more accurately, right? And so if you see kids do this, where they'll get on an escalator and they walk the opposite direction, and you see no movement, right? The vectors cancel each other. So this is the simple linear ones. If you've ever swam across a river or something like that, B would be let's say the flow of the rivers this way, and A, you get in and start swimming towards the other bank of the river, but your path really is the combination between the two, and is the R that you see here. And this is what's going to happen with our chemicals, right? This you could think of as water, where vector A is the OH bond in one OH in water, and then vector B would be the other OH, right? And so they add together, and the overall polarity vector that you see in water is the red one. All right, so just a couple others. They're kind of picking them at random. The 2D ones are obviously easier to see. These 3D ones can be a little tough. But probably what's most important is table 10.2 here. And notice you can tell what's important for us and for your future classes is all of these are where it's either 2, 3 or 4 groups on the central atom. It doesn't have the 5 and 6 groups on the central atom, because this is meant to really prepare you for OChem. Those other ones are mostly for chem majors and don't have as big of application. All right, so the top up here is this is CO2, right? Carbon's in the middle, 180. So it's linear, and the vectors are identical and cancel each other. The one on the right then is water, where less than 180 leaves it generic. So if it was the trigonal, it would be 120, and if it was the tetrahedral, then it would be 109. Right? And then water has hydrogen and then 2 lone pairs, and so water's probably it's more than 109. I forget what it was, 107 or 105 or something like that. I forget what it said on the slide. But the point is that it's bent. There's no way for the vectors to cancel each other, and so the molecule is polar. And this is why water does all the unique things it does versus, say, carbon dioxide. Why it's a liquid and expands when it freezes, so that means ice floats. And this has huge effects. So it sounds like, oh, that's, when I say that, you think, okay, so just my ice cube floats in my water just because of the lone pair. But it really has huge effects globally, right? So as things like what makes making ice float means that the sea levels stay the same, right? In summer and winter, there's more ice in the winter than in the summer. Lakes in places that are cold enough for water to freeze, they the ice floats up to the surface, and just the surface of the lake freezes, right? Not the whole entire lake, right? So fish and things that are alive below it don't actually solidify the whole lake like an ice cube. And that can occasionally happen places, and more things die. Not everything's prepared to live through the winter. But the North Pole there's no land there. So if all that ice melts, then that would have huge swinging effects on the sea level, right? So and there's quite a bit of other things that do this that you'll get into in Chem 162 in the next chapter. Okay, for trigonal pyramidal, right, when they're perfectly symmetrical, like tetrahedral and trigonal pyramidal, they cancel each other if all the bonds are the same. Right? If the bonds aren't the same, then they can't cancel one another. And this last one down here, this was our classic example. This was where nitrogen was the central atom, and that there's a lone pair up on top, which pushed the other three atoms down. So this one's always going to be polar. As long as there's polarity, you have to have a polar bond for the things to be polar, but there's no way for this one to cancel. All right, so let's go through and take some of our old views and Lewis structures, and then look at these the modelings in the 3D shape. And again, specific examples, right? So carbon dioxide, the bond is polar, right? Carbon is, the electronegativity is like, what is it, 2.5, and oxygen's 3.5, but anything that isn't a carbon-carbon or a carbon-hydrogen bond is going to be polar. So the individual bonds are polar, but our symmetry here, it's like two vectors pulling in opposite directions, and so they cancel each other. And the net result is that the molecule is non-polar. And then here's water, right? Those lone pairs are there. They're not drawn in, but we know that they're there. And they push down the two hydrogens. We get this bent type of structure. There's no way for these two to cancel each other, so the solid vectors add up, and the overall effect we see in the molecule is the dashed line. And so water is polar and has this huge effect on freezing points, boiling points, all kinds of things. This one isn't drawn as well, but if you get a model and then you can hold it and look at it at the same time. And it's hard to show in 3 dimensions on a 2-dimensional screen. It's a little hard to show it. But the nitrogen-hydrogen bond is polar, right? It's not carbon-carbon. It's not carbon-hydrogen. It's not nitrogen-nitrogen or hydrogen-hydrogen. So the bond's polar. There's the lone pairs up here at the top. So it's a tripod-like structure, that pyramidal, trigonal pyramidal. There's no way for the vectors to cancel. And so the overall effect is the molecule's polar. Okay, so like I mentioned, if you've ever been in a boat harbor, and it's, always happens in some way, boats have gasoline to make them go and oil for them to keep the motors lubricated and whatnot. So oil and gas always eventually gets spilled out on accident somehow. Their density is lower than water. Their density is like 0.8, and water's is around 1. So they're lighter, just like air bubbles or the way a blimp floats. So you'll see it on the surface of the water. And in organic chemistry, you'll use special pieces of glassware where you'll take water and some hydrocarbon and mix them. And the organic things that are polar will go into the water, and the things that are non-polar go into the oil. The organic, they call it the organic layer versus the aqueous layer. And this is basically the way a microwave works. So, right, you can think about a water molecule like a little magnet that has a north and a south. It doesn't really matter which you want to call which, but they orient with one another, where the negative lone pairs off the oxygen interact with the slightly positive hydrogens on the next water over. Then what a microwave does is it flips the magnetic field back and forth, and so the little water molecule turns back and forth and back and forth. And it basically warms your food up by friction within the food. And this is how soap works. So, right, if you get grease or dirt on your hands or something, you go to the sink and get some soap. You use the soap because you can't get the dirt or the grease. Grease is the best example. You know, if you've changed a tire on a bike or the chain on your bike, something like that. Water just won't on its own wash it off. And so what soap is it's just a molecule that has a polar group. And so remember the black is carbon, the red is oxygen. So you have this CO2 end of the molecule, then white is hydrogen. So the back half of the molecule looks like gasoline, like oil, and the front head, or the front part, they call it the head and the tail. The head part is polar, so it interacts with the water. The back part is oily or non-polar and interacts with the grease, and this helps you solubilize it and wash it away. Okay, so let's do a couple practice ones here. Which of the following are polar? So they already gave us the structure. And then in this one, it was nice of them to come in and give us the electronegativities. But if they're not bonds with the same element and they're not carbon-hydrogen, then the bond is polar. With the one exception when you go across trends is this nitrogen-chlorine one. Right, so the chlorine and nitrogen have basically the same electronegativity. So this nitrogen-chlorine bond isn't polar. And so then it just comes down to a single bond, so that's pretty easy. Nitrogen-oxygen, they're not the same atom. And so the bond is polar. It's the only bond that matters since the other bond isn't polar at all. So the one on the left is polar. Now, what about the one on the right? The way they have it drawn would make you think that there's a lone pair there, but there's not. This is just, I don't know how they drew this, but there's different programs for drawing molecules. And the point is that there's 3 electron groups. The atoms are all the same. The bonds are definitely polar, the SO. And then remember the resonance, this double bond really spends a third of its time in each location. So that lone pair means it's bent, but it doesn't really matter because this bond isn't polar. So there's the only polar bond. There's nothing to cancel it, so it's polar. The SO3, it's really trigonal planar, right? And then that double bond spends equal amount of time. Yes, the individual bonds are polar, but they actually cancel each other. So all the bonds are polar, but it's symmetric. And so the overall effect is that the molecule's non-polar. Ooh, problems. Let me think. Let me take a look. So what this is we go on to the next theory. And this seems like a good stopping point. I know it's a little bit early, but this is our last chapter we're going to cover, and we'll have a couple of weeks after the midterm. And so that leaves us where we have like 70 slides. And the last few slides aren't, they're like foreshadowing for future classes. And it just takes a little while to go through this next theory. And so I think it'd be best to leave that till the end. So this is our line in the sand, 70 to 71 for what'll be on the next midterm. Our next midterm is next Wednesday. And so Monday in class, we'll do the study guide that's up on Laulima, and then any extra worksheets that we can get to. The study guide, I usually have them set up where they take me about 50 minutes to go through. this is the first time I've had a Monday, Wednesday class that meets for, you know, the hour 15 or hour 10, hour 15, whatever it is. Anyway, so that's our plan for what we're gonna do. Should I pull up a calendar? Let me just pull up. All right, so here we are on today on the 12th, our exams on the 19th. Next week, Wednesday, we'll do the study guide and some worksheets. That then leaves us two, I think three, and then the last day of classes is that Wednesday. It might be the 4th, I forget offhand. But so then we'll finish up chapter 10 on the 24th and the 26th. Maybe go on to the first, depending on how long it takes to do those two. But then we'll definitely be reviewing on the 3rd, and maybe the 1st and the 3rd. And then our final is the week after. I think our final's on the 10th offhand. But I know the 4th and the 5th are study days. I'm not sure if the 3rd is. Well, I think we had a lot of holidays, so I'm pretty sure we have class on the 3rd. We'll review then as well, and then your final is on Wednesday. Okay, I know a few minutes early, but it'll take longer than 15 minutes to go through that next whole bonding theory, and then that forces, you know, more stuff that you're responsible for on this next midterm. So this seems like a good place to stop for the day. Let me hit the button. So I hit the button if you want to unmute, and kind of as usual, questions, comments, thoughts, feelings, etc.
Yeah, I have a question. Chapter 10, or no, I'm sorry. The PowerPoint chapter 11, liquid solids and intermolecular forces. That's, is that something we're going to be going, like, is that going to be part of the final?
No, that's for Chem 162. But
okay.
Sometimes people ask questions, you know, like we got to today, where the boiling points, melting points, the linear versus bent nature, and so when people take freshman chemistry, it's usually 20 chapters, and if we were on the quarter system, you would do about 7 chapters a class. But here we're on the semester, so we do about 10. It's still the same amount of material, but chapters 11 and 12 really build off what you learned in 10. So sometimes people ask a question or two, and so I have just 11 on there if you want to see, you know, what you're in for, a glimpse at what you're in for next semester, that kind of thing.
Okay, that's good to know, because I was gonna start on it, and I didn't realize. I finished the PowerPoint 10. So basically everything up until chemical bonding 2, that's everything that's going to be on the final up until then.
Well, where we finished today, the final, chemical bonding 2, and then where we finished for the first midterm. So the final will have the rest of where we stopped today on. It'll have a bigger emphasis on that. But I mean, if it depends on what you're doing. So like, there's a couple majors out there that don't need Chem 162, not very many. And so for Chem 162 people, they don't care about chapter 11, right? They never have to look at chemistry again. But for most everybody else, like engineering and like physics and math or whatever, they don't need OChem. So they are interested, you know, what's ahead in Chem 162. And like I've mentioned before, like I would recommend taking 162 over the summer while this stuff's fresher in your mind, because chapters 11 and 12 are just taking what you've learned in 9 and 10 and looking at the physical properties of them. So in here we look at the bonding and the shape and everything, and then the next 2 chapters are okay, what happens when you mix these things and the boiling points and the melting points and stuff. So, but for people who have to take OChem, which I think is a fair amount of the class, I know at a junior college, like you don't pick an official major, but for OChem, these last two chapters are really important because you're all you're going to do all year long is play with carbon molecules. And like I was mentioned, I think I mentioned before, in OChem, you don't even need a calculator for the test. Like it's not, you're not doing lots of math, or the math that they give you is things you don't need a calculator for. Like you divide 10 by 5, it's obviously 2. You don't need a calculator for that. So, yeah, anyway, I usually ramble when someone asks a good question. I ramble on a little longer than needed.
No, that's good. That's interesting because so and OChem is obviously after 162. Like I'm a biology major, so
Yeah.
that's definitely going to be one I need. But okay.
Yeah, so in OChem or in 162, it's pretty math heavy. So in 161, you basically learn about the molecules and like their shape and how they look. And then in 162, you do the math behind how they move and behave and whatnot. And so you need to know some of the math principles so that when they tell you a number that's like a rating, like system for the way an organic chemical behaves, you need to know the rating system, which you learn in Chem 162. But to draw the molecules all year long and understand the way their behavior and the way they're acting and the way they look, that's all this end part of Chem 162. So yeah, if you're a bio major, if you haven't already, just go buy one of those modeling kits on Amazon. It'll help you here, and then you're going to use it in OChem. It's, I mean, I like this stuff. Obviously, I got a PhD in it, and I don't understand how someone could pass OChem without a modeling kit. Like, unless you like love Legos and architecture and like you see really well in your mind and in three-dimensional space. You need the modeling kit to hold in your hand the molecule they're talking about, especially when you're first learning it.
Okay. Yeah, I wrote a note that says Amazon modeling kit, so I was listening.
Yeah. I mean, you can get them anywhere. They're probably at the bookstore if you have OChem. I don't know if there's OChem at. I haven't looked at the schedule of classes. I don't know. I'm on Oahu, so it's kind of weird to me. But some of the junior colleges offer OChem, and some of them don't. Most of them, I know a few students I still chat with that they're taking OChem now at one of the junior colleges, and the class is online, but you have to come in on the day of the test because you get out the piece of paper and you draw the molecules yourself. So I definitely hear that from students when they, especially these online days where they're just looking at the pictures on the test and you circle the right, ours is going to be multiple choice where you pick the right shape or I tell you the names of them and you pick it. And that's far different from OChem where you're going to have to, on a piece of paper and grab the pencil and draw it to where the instructor believes know the shape of it. So it's good to get that practice in here. If you're a bio major, if you're an engineer, you're going to take Chem 162 and that'll be the end of it. So.
Okay. And then I just had one more question. So the study guide, I'm finishing up all the worksheets in the study guide now since I did the PowerPoint already. And I noticed pretty much every worksheet up until 15, which is the last one, has stuff that I believe will probably be in part on this exam number 3. So basically, you're just going to do what you did before. Go over all the worksheets that have problems that pertain to what might be on exam 3. And then the study guide 3 on Monday.
Yeah, I'll do the study guide first and then go to the worksheets. And the worksheets, so the study guide, it's like I've done this class for years, off 161 off and on. So the study guide is very like, it kind of follows the history of this is that the whole system eventually made it where you can't give an exam 2 weeks before finals. And they made this a rule like 5 or 6 years ago. And then I didn't teach 161. I don't think I've only taught 161 once during COVID. So the worksheets were made up separately. So I don't know where the cutoffs in the worksheets are as well. Like you know, which number applies to our test exactly, because the way the worksheets were designed was it was a 4th hour where, like, you know, we meet for 3 hours in lecture like this, and then students would go with either a graduate student in a smaller class, and they would do the worksheet, and they were staggered throughout the day. So some people would have their 4th hour where they did the worksheet on Monday, and some people not till Friday. So if the test was on Wednesday, then, you know, the material on the sheet could be, you know, useful or ahead of the, you know, beyond the test, that type of thing. So I don't know the layout of the worksheets as well as can't speak to the, you know, if you've gone too far by the number on it. I don't have the best confidence in it like I do the study guide. So
I gotcha. I figured just doing them, I mean, practice, right? I did notice
yeah,
the study guide 3 has some stuff about like calculating wavelengths of light, which was our last exam, right? I mean, I did them
yeah,
anyways, but there's
yeah,
quite a few problems on there.
yeah.
So
Yeah,
just
so
kind of,
the cutoffs, yeah, the cutoffs too have been like when they make spring break. Like, I don't know who decides when spring break is exactly. You know, does the president do that or something? But normally spring break was always when Kuhio Day was. So it's weird to me to have Kuhio Day be a day we don't have class, because it was all like for a decade or something. It was always during spring break. To me, this is only like the first, maybe second time it hasn't been during the spring break week. So, but I don't know
I
if that,
gotcha. That makes sense.
yeah, I don't
That's
know.
probably why. Yeah.
Yeah, I don't know when Easter falls, like who decides that versus when spring break is. And, you know, anyway, it is what it is. So,
All right. Well, thank you for answering all my questions.
yeah, no worries. Good questions.
All right. Have a good day. Bye.
You too. Bye.
Hey, so I have a question. So how do you determine electronegativity of elements? Do you just have to look up a chart?
Yeah, it's basically from the periodic table. Let me see if there we go. So it's here in this table, and but you don't really need to have the table memorized, right? So it doesn't apply for metals. It's only these non-metals over here. And the bonds that are polar are the ones that have a 0.5 difference or greater. But notice, right, boron to carbon, it's a 0.5, carbon to nitrogen, a 0.5, nitrogen to oxygen, a 0.5, oxygen to fluorine. So every one of these bonds bonded to any other element is polar. The only time you run into an exception is like here, where you go chlorine to nitrogen. They're both 3, because you're going one with the trend here up and over, and one against it, right? We went over and down. So I don't put exceptions. I'm not trying to trick you. I don't want you to have, you know, this sheet taped up on the wall, this slide. I mean, you can if you want, but basically what it comes down to is prepping you for OChem, where any bond between the same 2 elements is nonpolar, and then hydrogen and carbon is nonpolar as well. And basically every other bond is going to be polar. So if it isn't, you know, carbon carbon, nitrogen nitrogen, you know, oxygen oxygen, whatever, the same bond, and then carbon hydrogen, every other bond besides that is polar.
Okay.
Yeah.
Thank
It's
you for that.
meant to try to simplify things. So when they put it in here, they put these differences, and that makes it seem like you need the chart. But when you, I think there was a slide in here. There isn't. No, sorry, it's in Chem 162. But if we go to this, right, there's no reason to put the chart in there for the metals. They're all way up here, right? The ionic ones. So there's really no reason in the chart to have all the full table in here. It doesn't matter. The only ones it matters for is hydrogen, you know, over to iodine. This little triangle, this little corner of the periodic table is the only thing it applies to.
All right. Okay. Yeah.
Yeah.
All right. Have a good one.
All right, cool.
See you Monday.
Professor.
Yeah.
Bye.